Welcome to video 3 of the fundamental theorem of calculus. I asked you to maybe try letter D and F, and if you did, I have the solutions right here for D and for F. We're just setting up the fundamental theorem of calculus formula as a way to evaluate the definite integral exactly, right? So when I get to the bottom three, so here I am not given the graph. I'm sorry, I'm not given the table of values, I'm given a graph. And this is the graph of g of x. It has 3 line segments. Using the graph of x, let's find the following. Okay, here we go. To find the definite integral of g prime of x dx from -1 to +3, we're going to take the antiderivative of g prime of x, meaning we're going to find the function whose derivative is g prime. Well, that would be g. And we're going to evaluate the top limit of integration. And then we're going to evaluate the bottom limit of integration in the same function, and then find the difference. Subtract the two. In that order, right? Top minus bottom function value. But this is the graph of g. So that means if I'm looking for g3, g3 would be 1, and g of -1 would be 3 minus 3. So my answer here is -2, right? So g of 3, the function value at 3 is 1. G of -1, the function value at -1 is 3. And if we subtract those in that order, we get -2, and that's what we need. Okay. What would be the definite integral of g of x dx from 6 to 1? Well, here I notice the integrand is the function that we're given, and the function that we're given is made up of line segments. So we could use the original the original method of breaking up these shaded regions into geometric shapes. And so what we're going to do is we're going to look at this as shaded region under the curve. I will say I noticed that the bottom limit is the bigger value, so I'm going to go ahead and switch them. Remember, you can switch the limits, but you're going to get the opposite answer. So we're going to find g of x dx from 1 to 6, from 1 to 6. Remembering that whatever I get, my answer will be the opposite of that because I went backwards from 6 to 1. The original setup is from 6 to 1. Let's see. Well, I can break this up into a rectangle whose base is 3, the height is 1, so therefore the area is 3. Excuse me. And I can set up this as a trapezoid whose base 1 is 1, whose base 2 is 3, and whose height is 2. So remember the formula for the area of a trapezoid is 1/2 times the height times base 1 plus base 2. Or you can say the average of the heights times the base. Either way, you're going to get 4. So therefore, this particular integral is -7 because I had to, well, I guess I didn't have to, excuse me, but I switched the limits of integration, which switched the signs of the integral value. But I can figure out the areas by just finding the area under the curve, which was the original way of finding definite integrals. Okay. Excuse me. As we get to letter 6, we notice letter 6 has 2 terms in the integrand. So I'm going to split it up. We're going to take the integral from 5 to 6 of g double prime x dx minus, we're going to take the integral from 5 to 6 of 4, and my bad, this should not be subtraction, this should be addition, 4 dx. Remembering that when we have a constant, this is really just the area of a rectangle whose height is 4 and whose base is the difference in the limits of integration, the delta x between 5 and 6. But over here, we're going to need to take the antiderivative, or the function whose derivative is g prime. Well, that would be g double prime. That would be g prime evaluated at the top minus g prime evaluated at the bottom limit of integration. Well, wait a minute. We are not given the graph. We are not given the graph of g prime. We're given the graph of g. So what does g prime of 6 represent? Oh, it represents the slope of this graph. So when I'm looking for this, I'm really looking for the slope at 6. At this point, what would be the slope of this line? Well, it looks like it's just 1. So g prime of 6 is 1 minus g prime of 5. Well, that would be here. What would be the derivative there? The derivative would be 1 plus whatever I got over here, which would be 1 times 4 is 4. And so my final answer is 4. Remember, the bottom line is when we are trying to evaluate definite integrals, if we can find the antiderivative, the function whose derivative is whatever's inside the integrand here of the integral, then we can do this difference finding of the antiderivative evaluated at the top limit minus the antiderivative evaluated at the bottom limit. And if we take the difference, that's going to give us the exact area under the curve, the exact definite integral value.